As can be seen on this slide, where we've got a series of illustrations of primate penises. Now, this rapid evolution leads to exaggerated structures like spines, different appendages, extensions, exaggerated curvatures. But divergence in structure is not limited to external morphology of genitalia, as structures inside of the penis evolve rapidly as well. Probably the most notable example of this in mammals is the baculum, which is a bone that resides within the distal end of the penis, otherwise known as the glans. So here I've got a collection of drawings of baculum from various carnivore and rodent species. So of course, they're not drawn to scale, but they are oriented in the same direction. So the base of the bone is here on the right side, and the tip or distal end is on the left-hand side of the slide. These bones evolved so rapidly that they're commonly used as a taxonomic marker, meaning that they're among few, if not the only morphological trait that allows one to discern closely related species. This rapid evolution leads to distinct morphologies, as can be seen in our raccoon and baculum curvature up here, or exaggerated cartilaginous extensions, as are common in rodents, is exemplified in our pitchfork penis bone of the bull. So, regardless of all of the similarities, or all of the differences, sorry, there are no similarities. All of the differences in morphology, they have one critical trait in common, is that every baculum enters the female's reproductive tract during copulation, yet we don't understand the function of these bones. Now, it's not from a lack of interest in studying bacula. Mammalogists have been keenly interested in trying to understand how these bones function for centuries now. And I've summarized some of those studies here in this table. So let's just look at the first line for a specific example. The hypothesized function is that the baculum works to protect the urethra during copulation. Based on that hypothesis, you would predict potentially that species with longer intermissions should have longer baculum. But when you test this in different mammalian groups, you get inconsistent results. So that prediction is supported in some carnivore species and primates, but not in other carnivore species. So this is the real trend when it comes to trying to apply a particular hypothesized function to all baculums, is when you look between mammalian groups, there's no consistent result. So why is this happening? Why is there no universal correlate to mating ecology and baculum function? Well, here are some of the possible explanations for that. First is that the baculum may just function as species-specific context. The second, and this is one of the issues in studying baculum function in general, is that most of those experiments focused on length instead of shape. And it could be that baculum shape is more critical for function. That's actually been shown to be true in some mouse studies. And the third explanation, which is what I'm going to be talking about for the remainder of this presentation, is that the baculum could have evolved multiple independent times. And if that's true, then studying between groups violates the fundamental assumption of a comparative study, and that is that the bone is a homologous structure, which it very well may not be. So, I want to make it clear that in studying homology of the baculum, we're not necessarily interested in telling you or trying to decide how many times exactly the bone evolved, but we just want to see if it evolved a single time or more than once. In order to do this, we went through a twofold approach, the first of which was an extensive literature search for baculum presence and absence. Now, there are a lot of generalizations made about what orders of mammalia have bacula. We wanted to avoid any of those generalizations. So, to be included in this study, a species had to have either an illustration, measurements, or histology of the cross-sectional histology of the penis showing that there's actually a bone in there. And for an extreme example, in picas, they actually had at the bottom is an example of the table of pretty much our data. It's relatively simple, where we have an order that the species belongs to. We've got dogs up here, spotted hyenas in the middle, and then cats at the bottom. And then we have two character states, and that's it. You either do have a baculum or you don't have a baculum. So to assess the evolution of this bone using a phylogenetic approach, we first started out with a family-level phylogeny used as a scaffold to merge our 5 taxon-specific phylogenies. We're then able to calculate the probabilities of the two character states at all internal nodes and evaluate the evolution of the bone based on those probabilities using 1,000 iterations of stochastic mapping. So here are our results. I don't intend you to read any of this, but just to get general trends from this. And for the remainder of my talk, I'm going to be using the red-blue color scheme. Red means that there's a baculum, blue means that there's no baculum. So, on the left-hand side, we've got the summary of our 954 species, and then the right-hand side is subdivided into clades where the baculum evolved in greater than 50% of our simulations. But to better illustrate this, I'm going to focus again on carnivores. So we've got our individual boxes which roughly tell you where the baculum was either gained, if it's a red box, or lost, if it's a blue box. And then the proportion of our 1,000 iterations of stochastic mapping in which that gain or loss occurred along this phylogeny. And as you can see, if we go back to our spotted hyena example, it's intuitive that the baculum was lost along this branch since this clade of hyenas and related species is surrounded by red branches or species that do have baculum. So to summarize our gains and losses, we're able to find that the baculum evolved a minimum of 9 times and was lost a minimum of 10. Now some of these gains are within a single species of the order. Sure, an example of that is within lagomorphs. Picas are the only species that have baculum. Another interesting thing is that rodents have a single gain of baculum. And all of the species of rodents that we're able to find through our literature search have bacula. So it seems like 487 species that were included in this study, all of them have bacula. It originated early in the rodent ancestor and has since been maintained and diverged in shape. There are other groups like primates or bats where there are multiple gains and multiple losses. Yet we don't understand what's driving the maintenance in rodents or gains or losses in any of these. In order to address the robustness of our results, we implemented 3 bootstrap methods, of which I'm showing one here. So what we did is go through our 954 species and subsampled at 90, 80, 70, 60, and 50% of our data set. And here in our diamonds, I show that we have, these are the results of our stochastic mapping where we have 9 gains, 10 losses. And you can see that even when we get down to half of our data set, that we get similar inferences, that the baculum evolved more than a single time. So to conclude that part of my talk, we're able to show that the baculum has evolved a minimum of 9 times, making it a non-homologous structure, meaning that comparative study between those independent derivations violates the fundamental assumption of comparative studies. So it's not what we should be doing to understand the function of this bone. So how do we actually address the function of the baculum? How does this evolve independently so many times? Well, we're thinking that it could be through co-option of developmental pathways or through novel developmental pathways every single time. I'm not sure what exactly is going on, but in order to get to the core of that question, we started with some preliminary studies looking at transverse rodents, so these are independently derived, meaning the ferret is of the carnivore order, independent derivation of baculum from both rats and mice. The first thing I want to point out is that you could elucidate some sort of function of the baculum just by how expansive the bone is. The ferret baculum takes up a lot of the soft tissue space, whereas the rat and mouse bacula seem to be not as impressive as the ferret is. There are also differences in terms of trying to understand like the biomechanic function of these bones. The first of which is the open space in bones, which is how a lot of biomechanic function in long bones is assessed. So the extent of this medullary cavity represents the bone could be important for us to understand what these bones do in sexual reproduction. Another point is that these bones don't develop in the same fashion. Sometimes they have a single zone of ossification, and sometimes they have multiple zones of ossification. So here in the yellow, I'm showing that there's a cartilaginous region at the distal or tip of penis bone. And it's not very impressive here in the ferret, and you can see a little bit of it in the mouse. But in the rat, it's not only a big portion of the baculum itself, but within an independent derivation, or within the same derivation in rodents, it's mineralized in rats and still cartilaginous in mice. So even within these independent derivations, there's a lot of room for this rapid evolution to occur. So these are some of the first steps that we're taking to try to understand the development and the origins of bacula in different species. And we'll probably continue on with